Today we will be learning about primitive Pythagorean triples. The primitive Pythagorean triples challenge problem, which we will be solving today, is a mathematical inquiry regarding the number of these triples having value under 100, 200, and 400. A Pythagorean triple is a group of three positive integers, x, y, and z, with x squared plus y squared equaling z squared. The term Pythagorean is familiar to students because of the Pythagorean theorem, which states that each side of a right triangle must have side lengths that satisfy the equation x squared plus y squared equals z squared. A Pythagorean primitive triple, however, is one in which the greatest common factor of x, y, and z is 1. We begin this problem by transforming this equation. Let's rewrite this problem and begin to transform the equation. X squared plus y squared equals z squared. The Pythagorean theorem again. We begin by subtracting y squared from both sides, leaving us with x squared equal to z squared minus y squared. The next step is to simplify the right side of the equation to z plus y times z minus y. This is still equal to x squared, however. The next step is to divide both sides of the equation by x squared. The left side then simplifies to 1, with the right side simplifying to z over x plus y over x times z over x minus y over x. Because these two terms multiply together to equal 1, they are reciprocals. Thus, let us have AB represent z over x plus y over x, and b over a represents z over x minus y over x. Let's now solve for z over x or y over x. Let's erase this and start the problem at the top of the board. As we wrote before, z over x plus y over x equals a over b. To solve for z over x, we must solve for y over x so that can be substituted into the equation z over x minus y over x equals b over a. Let's begin. The first step is to subtract z over x from both sides. This leaves us with y over x equal to a over b minus z over x. This can now be substituted into this equation. This gets us z over x minus a over b minus z over x equal to b over a. Because the subtraction sign is in front of the parentheses, it must be distributed to both terms. This results in z over x minus a over b minus z over x, which equals plus z over x, equaling b over a. Z over x can then be added to z over x to equal 2z over x minus a over b, equaling b over a. The next step is to add a over b to the right side. A over b plus a over b on both sides, equaling 2z over x equal to a over b plus b over a. The final step in this solving is to divide by 2 on both sides. This leaves us with z over x equal to 1/2 times a over b plus b over a. Now that we have solved for z over x, let's solve for y over x. Let's erase all this work. As we did for the previous equation for z over x, we must now once again start by solving for the opposite. This time we must solve for y over x in the beginning. Let's rewrite our equations. Z over x plus y over x equals a over b. Z over x minus y over x equals b over a. As I said before, we must now solve for z over x. We begin by adding y over x to both sides. This results in z over x equaling b over a plus y over x. As we did before, this equation for z over x can now be substituted into this equation. This results in b over a plus y over x plus y over x equals a over b. This now equals b over a plus y over x plus y over x equals a over b. Once again, we can add y over x plus y over x to get 2y over x plus b over a equaling a over b. The next step is to subtract b over a from both sides. Minus b over a and minus b over a. This results in 2y over x equaling a over b minus b over a. The final step in this equation is to divide both sides by 2. Divide by 2 and divide by 2. This can now be simplified to 1/2 a over b minus b over a. Let's now erase this work and look at both equations next to each other. Okay. Let's remember that y over x equals 1/2 times a over b minus b over a, and z over x equals 1/2 times a over b plus b over a. As we look at these two equations, we now notice that they can be simplified even more. The first step is to find a common denominator. The common denominator for this one is a over b. We thus simplify it to 1/2 equal times a over b times a minus b times b over a times b. This would then reduce to 1/2 times a squared over ab minus b squared over ab. This can then once again reduce to 1/2 times a squared minus b squared over ab. We then must multiply 1/2 by this term. This would equal a squared minus b squared over 2ab. The same process can be done with z over x. We must first find a common denominator, which is once again ab. We simplify to 1/2 a times a over b times a plus b times b over a times b. This can then reduce to 1/2 times a squared over ab plus b squared over ab. This can once again reduce to 1/2 times a squared plus b squared over ab. We must then once again multiply by 1/2 to get a squared plus b squared over 2ab. These equations look very similar. The only difference is the addition sign compared to the subtraction sign. Because this one equals y over x, and this one equals z over x, we now know that x equals ab, y equals a squared minus b squared over 2, and z equals a squared plus b squared over 2. We can now use this information to solve for a primitive Pythagorean triple. However, before we begin to solve for a primitive Pythagorean triple, we must first know some rules about a and b. First, a must always be greater than b. X must always be odd. X must always be odd because either x or y must be odd, because if both were even, then their greatest common factor would be 2, but it must be 1. Thus, to make matters simpler, we will always have x equal to the odd value. Because x is odd, a and b must also be odd, because the only way to obtain an odd number is to multiply two odd numbers. In addition, a and b must be relatively prime, because they make up x, which is relatively prime with y and z. Let's begin to solve for a primitive Pythagorean triple. Let's erase this work. We will have a equal to 3 and b equal to 1. Thus, x equals a times b, which will be 3. X equals 3. Y would then be 3 squared minus 1 squared over 2, equal to 9 minus 1 over 2, or 8 over 2, which is equal to 4. Z would then be 3 squared plus 1 squared over 2, or 9 plus 1 over 2, equal to 10 over 2, or 5. Thus, we have found our first primitive Pythagorean triple, which is 3, 4, 5. We will now reference a table showing all of the Pythagorean primitive triples under 100, 200, and 400. As you can see, this table represents the same rules that we just found. A must always be greater than b, with b always less than a. Y over z is equal to b times b. As you can see in column 7, the change in y over and z should be 7 times 7, or 49. Now let's look at this one, 77, 36, 85. As you can see, 85 minus 36 is in fact 49. As you can see, there are some blank spaces. There's one right here at 9 and 3. This space is here because 3 and 9 share a common denominator of 3. Thus, they cannot equal a primitive Pythagorean triple. As you can see, this table is also color-coded. The green color represents all the primitive Pythagorean triples under 100. The green and blue represent the ones under 200. And the green, blue, and red represent the ones under 400. In support of these results that we have just solved for, there are many websites containing the same answers. In fact, the mathematician Euclid has a book, Elements Book 10, which has a proposition inside of it. The proposition 29 talks about Pythagorean triples. In fact, he himself found the same results that we found today. Thank you. I hope you enjoyed the lesson.